Okay, on to section 1.5 and exponential functions. So this section is a pretty quick review of some of the material from Pre-Calculus 1. See, for example, if you'll click on the link here in the PDF that's posted online, that'll take you to the actual pre-calculus notes for exponential functions. We'll deal with these again in chapter 7 in a cleaner way when we define log and exponential functions using calculus. But for now, we'll take a pre-calculus approach to exponential functions. And we'll see a handful of applications involving population growth, spread of disease, continuously compounded interest, radioactive decay is a big thing for exponential functions. We'll certainly do an example to illustrate that. So formally, the definition of an exponential function is take a not equal to 1 to be a positive constant, then the function f of x equals a to the x power is the exponential function with base a. So let's look at a couple of quick examples in the supplements where they ask us to the best of our admittedly limited ability, graph y equals 3 to the x. Okay, so we'll make a table of values of powers of 3, where the exponent takes on the values -3 through +3, so those integers. So if we look at 3 to the -3 power, the negative exponent means take a reciprocal, so we get 1 over 3 cubed. 3 cubed is 27. 1 over 27, -2, 3 to the -2 is 1 over 3 squared, so 1/9. 3 to the -1 is 1/3. Anything to the 0 is 1 except for 0 itself. And then these powers of 3. If we plot those points, and we see it grows pretty fast, so plotting it to scale, we get something along these lines. So the graph grows like crazy. I can't even fit the point 3, 27 on here. So 3, 27 would be somewhere up here. But we get the usual shape for an exponential curve, something of this sort. Okay, I actually can't even fit 3 squared on here to get the 9 out. So let's see, to scale, we get a point out somewhere up here. This function grows exponentially fast. So it triples every time we increase the input by 1 unit. It's an exponential function involving powers. So base is 3, it triples every time we increase the input by 1. Graph. Question number 8a from this section, sketch the shifted exponential curve y equals 3 to the x plus 2. Okay, chapter 1, section 2, I think it is, deals with these ideas of shifting curves around. We're looking at y equals 3 to the x plus 2. Well, we'll simply shift the graph of y equals 3 to the x up by 2 units because of the plus 2 thing. So that'll take what we had on the previous slide, shift it up 2 units. On the previous slide, we had a horizontal asymptote over to the left-hand side of y equals 0, the x-axis. Well, we've moved everything up 2 units, and now we have the line y equals 2 as a horizontal asymptote of this particular function. So same thing we had on the previous slide, just shifted 2 units up. Shifting of a graph by adding a constant to the function values. Back to the notes. So all's well and good. If we raise these bases to integer powers, like we just did with the powers of 3, in general, if x equals, say, n, an integer, if that integer is 0, then a to the x power, a to the 0 power equals 1, provided a is not 0 itself. We won't look at exponential functions base 0 or base 1 for some technical reasons, though the base 1 ones are always defined. So if we want to take a positive real number and raise it to the nth power, where n is an integer, that simply represents repeated multiplication. So what we'll get out if we take a to the x power, a to the n power, that is, x equals n. If n is a positive integer, it's just repeated multiplication. Multiply a by itself n times. If n is a negative integer, then we got to avoid a equals 0 for sure in this case because we get reciprocals. The negative part of the exponent means take a reciprocal. So what we get is 1 over a times 1 over a times 1 over a, absolute value of n times. For example, if n was -3, we'd have 1 over a times 1 over a times 1 over a 3 times. We'd have 1 over a cubed, as expected when the exponent's -3. So no problem raising any real number to an integer power, except for 0 to the 0, which is undefined. It's equivalent to dividing by 0, so you can't do that. What about fractional exponents? Suppose x is p over q is some rational number that is a ratio of integers where p and q are integers. Then a to the x, that is a to the p over q, is by definition the qth root of a to the p power. You got any problems here? Can you raise a to the pth power where p is an integer? Certainly. Avoiding that 0 to the 0 thing? Certainly. We'll do it as described above. How about taking qth roots? Well, that could potentially cause some problems because, for example, we can't take square roots of negatives. And so we can't take fourth roots of negatives or sixth roots of negatives. We can't take even roots of negatives because it involves complex numbers. So there are some disclaimers to go on this about certain algebraic things we can't do. We cannot divide by 0 because nobody can, and we will not take square roots of negatives because we're restricting ourselves to real numbers because we got enough problems without worrying about complex numbers. So there's some constraints here in terms of which numbers can be raised to a rational power, p over q. If a is positive, we got no problems at all. And when we were defining exponential functions, we were taking the base a to be a positive constant. So we've got no concerns when a is positive with any of these. So this takes care of integer exponents. This last comment takes care of rational exponents. What about irrational exponents? What if x is the exponent we're talking about here, what if x is irrational? Rather a long story, actually, but what we could do is take a decimal representation of x, which would be non-repeating and non-terminating, and do some successive approximations. For example, suppose we wanted to raise 2 to the square root of 3 power. What would it mean? Because the square root of 3 is irrational. So I can't do it in terms of raising to integer powers and taking roots. We could approximate. We could say, well, the square root of 3 is approximately this thing here to a whole bunch of decimal places. So we could say 2 to the square root of 3 should be, let's say 2 to the 1 or 2 to the 1.7 or 2 to the 1.73, 2 to the 1.73 listed here, and just keep adding these decimals to that exponent. You're adding a finite number of decimals, so you're dealing with a rational exponent. So we know what that means. We just defined that on the previous page. A dot, dot, dot. So what I could do is maybe say 2 to the square root of 3 is the limit of this sequence, whatever a limit is. You don't know what a limit is because that's a calculus thing. Limits of sequences will be defined in calculus. We'll define limits of functions in calculus 1. Limits of sequences is defined in calculus 2. So we got some concerns over what to do when we have irrational exponents. Are you sure this limit even exists? Well, that's kind of a long technical story. It's the axiom of completeness that guarantees that such a limit will exist. I encourage you to read and watch the video on Appendix A6, where we go through and talk about the axiom of completeness in terms of an airplane taking off. That's not really hands-on to this particular conversation here, but is definitely relevant to this conversation here. Okay, now we graphed y equals 3 to the x in that previous exercise. What we've got below is a graph of this function along with several other exponential functions. So what we've got in this picture down here is a graph of an exponential function. Let me make the picture big enough to see. I can't see the words at the same time, but okay. Here's a graph of y equals 2 to the x in blue. Here's a graph of y equals 3 to the x in red. And notice they don't even go all the way over to 2. If they did, they'd be getting out a number up here. So this thing's going to grow like crazy. Same problem we had in our picture. And here's a graph of y equals 10 to the x. When we plug in 1, we get out 10 to the first power. When we plug in 2, we get out 10 to the second power. So I got to go and find 100 on this scale. Geez, it's 10 times this distance here. So by the time we reach 2, this function's going to be way up there. The y value will be huge on this scale. So here's what the graphs of some exponential functions look like. An exponential function with base 2 in blue, base 3 in red, base 10 in yellow. So let's see, standard exponential functions. In the right-hand part of this image, the functions y equals 10 to the negative x, y equals 3 to the negative x, and y equals 2 to the negative x are graphed. For the conversation at hand, I'd like to change that a little bit. And instead of calling these y equals 10 to the negative x, let's take that negative exponent, put it on that 10, and think of this as 1/10 to the x power. 3 to the negative x, let's think of it as 1/3 to the x power. 2 to the negative x, 1/2 to the x power. So that these three functions we're going to look at on the right, they're actually exponential functions where the base is 1/10, 1/3, and 1/2. Remember, we looked at exponential functions base a, where a was positive and not 1. Well, something happens when we look at exponential functions where the base is greater than 1. They look like this and they grow like crazy. The bigger the base is, the faster they grow. And when the base a is between 0 and 1, like I say it is for these three, they're decreasing functions. Here we've got in blue 1/2 to the x power. Take that negative, put it on the 2, as just discussed. I would treat the red one as 1/3 to the x power and the yellow one as 1/10 to the x power, so that these look like what we've defined as exponential functions. And what happens when we have a base between 0 and 1 is they're decreasing functions. And the smaller the base, the faster they decrease. This one's decreasing. The yellow one is decreasing faster than the other two, red from left to right. Yeah, it's because it's base 1/10, right? The base is 1/10 here, which is a lot smaller, say, than 1/2. So here's what exponential functions look like. On the left is what they look like when the base is greater than 1, and on the right is what they look like when the base is between 0 and 1. Some rules for exponents, which I'm sure you're familiar with. We'll take these bases, a and b, both to be positive, so we don't have to worry about any division by 0 with the a's and the b's. The following rules hold true for all real numbers x and y. A to the x times a to the y equals a to the x plus y. Multiplying with the same base, add exponents. A to the x divided by a to the y is a to the x minus y. Subtract exponents when dividing. A to the x parentheses to the y power is the same as a to the y parentheses to the x power, or a to the x times y, the condition under which you multiply exponents. A to the x times b to the x is the same as ab to the x, sort of a distribution type property. And a to the x divided by b to the x is a divided by b to the x. So all of these just involve combining exponents in some sense, or almost a distribution type behavior of exponentiation. And all of these should be rules of exponents that you're familiar with. We'll give a proof of these, oddly enough, in chapter 4, after we've done the mean value theorem, and after we have a cleaner grasp of what an exponential function is. But we'll prove these using differentiation properties, it turns out. But you're familiar with these from the past, though you probably haven't seen a proof of them in the past. Let's look at exercise 1.5.12 next. Okay, use the law of exponents to simplify 9 to the 1/3 times 9 to the 1/6. Okay, not a hard problem. Let's use rules of exponents, part 1, that said a to the x times a to the y is a to the x plus y. Here we've got a equals 9, the base is 9. One of the exponents is 1/3, the other exponent is 1/6. Add those exponents together. 9 to the 1/3 times 9 to the 1/6 is the same as 9 to the 1/3 plus 1/6. 1/3 plus 1/6 is 1/2. 9 to the 1/2, that's the square root of 9. So the answer is 3. So easy enough there, properties of exponents. Back to the notes. We're going to talk about this natural exponential function. What's natural about it, we will elaborate on in Calculus 1. You've probably dealt with this in pre-calculus before. It was called a natural exponential function then. And it seems like the most unnatural thing to consider. Well, the naturalness is a calculus thing. So you really can't be told what's natural about the natural exponential function until you encounter calculus. So the number e, we'll formally define this in chapter 7. Earlier than that, we'll have a way to represent it as a limit. The number e is an irrational number, which is approximately 2.718281828, blah, blah, blah. Approximately. It's an irrational number. The decimal expansion goes on forever without any particular pattern, just like the square root of 2 and just like pi. An exponential function with this natural number e is called a natural exponential function. All right. It's a key on the calculator. Funny thing, any exponentiation you do on a calculator, it's done with this thing here and then converted to whatever you ask it. You ask it to take 10 to the 7.145 power, it's going to compute e to the 7.145 power and then convert that into base 10. So there is some naturalness and convenience in computation, if you like, for exponential functions base e. All stuff I can't explain at this stage. Calculus 2 will elaborate on it a little bit more even. All right, so to motivate as best we can with what we know now, this number e is alleged to be between 2 and 3. It's 2.718 something or other. So somewhere between 2 and 3, a little closer to 3. We expect the graph of the natural exponential function to lie between, quote unquote, probably should say, between the exponential functions 2 to the x and 3 to the x. All right, what we got in the picture here is a graph of y equals 2 to the x, a graph on the right of y equals 3 to the x, and in between a graph of this e to the x function. What they've done, and we'll make a big deal out of this in this early transcendentals edition of the book, is they've drawn attention to the slope of a tangent line to this smooth curve at x equals 0. So they've gone up here and they've drawn a line tangent to y equals 2 to the x at x equals 0, y equals 1. And they say the slope of it's about 0.7. Over here at 3, they've done the same thing. And this one will be steeper. Remember, bigger base, steeper function. And here, they've drawn a tangent line. All these exponential functions will pass through the point 0, 1. A to the 0 is 1, as long as a is not 0, and it won't be. And they've drawn a tangent line through the point here, and they say the slope here is about 1.1. Well, this blue curve, the exponential curve, should be a little bit steeper than y equals 2 to the x and a little bit less steep than y equals 3 to the x. And it turns out, bad math explanation, but it turns out if you'll draw a tangent line to y equals e to the x at 0, that is through the point 0, 1, it will have a slope of 1. And that nice, neat slope of a tangent line is related to the naturalness of the natural exponential function. That's all I got in terms of motivating the naturalness. We'll see this a little bit more when we consider the exponential function and differentiation in section 3.3, and we will do that in calculus 1. So the naturalness is related somehow or other slopes of tangent lines. There's computational ease when you do things with a natural exponential function or a natural log function that isn't there with other bases of exponentials and logs. So quite often when we consider exponential functions, we'll consider natural exponential functions. Exponential functions y equals y sub 0 e to the kx, where k is a non-zero constant, are frequently used for modeling exponential growth and exponential decay. If k is greater than 0 in this exponent, then it's exponential growth. If k is negative in this exponent here, then we're looking at exponential decay. So radioactive decay, for example, is modeled with exponential functions like this. Carbon dating works with exponential functions. So let's do a couple of examples to illustrate that. Exercise 1.5.30, population growth states, the population of Silver Run in the year 1890 was 6,250. Assume the population increased at a rate of 2.75% per year. In other words, we're taking the k value to be 2.75% converted to a decimal, so 0.0275. Estimate the population in 1915 and 1940. Okay, so the population growth is given by this exponential function where the k value is 0.0275. Y sub 0 represents the population at time t equals 0. We know the population at time 1890 was 6,250. So let's take y sub 0 to be 6,250, and we'll let t measure time in years after 1890. So in 1890, t equals 0. We plug in 0, we'll get e to the 0, which is 1, and we'll get y equals y sub 0. That is y equals 6,250. So we're starting the clock at 1890. That's what's being accomplished with this. And that's why the sub 0, time equals 0. We get the population out as desired. So the model we're dealing with is y equals 6250 e to the 0.0275 t. So y is a function of t, the k is a constant, it's that value. Y sub 0 is a constant, it's that value. So that's the model. They wanted to know the population in 1915 and 1940. All right, 1915. T equals what in 1915? Well, we started the clock in 1890. This is 25 years later. So in 1915, T is 1915 minus 1890. That's 25. Units are years. It means K would have to be expressed in per years as well. And they said something about per year up here. I've been arguably remiss with the units in this one. So the population at that time is 6250 e to the 0.0275 times t. T is 25. I feed that to the calculator and get approximately, to the nearest integer, 12,430. Okay. How much did the population go up by? It went from 6,250 to not quite twice that. Double 6,250 and you get 12,500. We got a slightly less than that. So the population has slightly less than doubled in that amount of time. What's next? 1940? Okay. In 1940, what's the t value? Well, 1940 minus 1890 is 50. So we'll plug 50 in for time. Same thing we had before, except we've replaced the 25 with a 50 in the model. And I crunch the numbers and I get 24,719. How's that relate to this population previously? If I were to double this, we get 24,860. You know what? That's slightly less than twice this previous population. So here's what's happening. Every 25 years, this population is almost doubling. Not quite. We got the slightly less than half in each case. So from 1890 to 1915, the population almost doubled. From then until 25 years later, it almost doubled again. What will the population be 25 years after that? Probably in the neighborhood of about 49,000, slightly less than twice this, and so forth. So what's happening is there's a doubling time associated with this. If we do population models, and I don't think we'll do too much with population models, maybe you've seen this in pre-calculus, these exponential functions come with a doubling time. When we've got exponential growth, there's a constant doubling time. Just like when you have exponential decay, such as in radioactive decay, there's a halving time. It's called a half-life when you have radioactive decay. Half-life when the thing is decreasing, doubling time when the thing is increasing. Populations usually increase exponentially under ideal environmental conditions, and there's more sophisticated models in exponential growth for population. Apropos to the current situation, so I'm making the videos in the middle of the COVID-19 pandemic, we'd expect the number of cases to grow exponentially initially. And so there's a doubling in number of cases, though in the long run, that can't be sustained. And so the population, the number of cases would have to level off, something called logistic growth. So one way to model exponential growth, or one way to model populations, is with an exponential model. It's unrealistic in long term, might be realistic in the short term. And there's other models out there that take into consideration such things as a carrying capacity of an environment. But this is plugging numbers into an exponential function. And the thing to note from this is every 25 years, it goes up by about the same proportion. That's a property of exponential growth. Here's a quick little example involving exponential decay. It's a long story, but it involves simply exponential decay. Laboratory experiments indicate that some atoms emit a part of their mass as radiation, with the remainder of the atom reforming to make an atom of some new element. For example, radioactive carbon-14 decays into nitrogen. Radium eventually decays into lead. Two examples. If y sub 0 is the number of radioactive nuclei present at time 0, the number still present at any later time t will be given by this. Y equals y sub 0 e to the negative rt, where r is positive. Okay, the exponent's negative, the r value is positive. So we have an initial amount, and this represents exponential decay of that initial amount. The number r is called the decay rate of the radioactive substance. It plays a role similar to the role of k in that previous example where we had the growth rate of a population. For carbon-14, the decay rate has been determined experimentally to be about r equals 1.2 times 10 to the negative 4 when t is measured in years. Predict the percent of carbon-14 present after 866 years have elapsed. Percent of carbon-14 present, that is, percent of the initial amount present after 866 years have elapsed. So, first off, let's take this r, 1.2 times 10 to the negative 4 value. Of course, we'll write that as 0.00012. So here's the r value. And they told us when t equals 866 years, predict the percent of carbon-14 present of the original amount. So they didn't tell us how much we started with, and they didn't ask us for an amount here. They asked us for a proportion, a percent of how much is left. Okay, so we'll plug in the r and the t value into the model. That'll give us y equals y sub 0 e to the negative r t for those values of r and t. Simplifies down to e to this thing here. I get the calculator out to 4 decimal places. That exponential is 0.9013. You started with y sub 0, carbon-14. 866 years later, you've got 0.9013 of y sub 0. So, how much of the original carbon-14 is left? 0.9013 is the amount. We'd convert that into a percent and get 90.13%. So about 90% of the carbon-14 is left, and about 10% of it has decayed away. Where'd it go? They tell you up here that carbon-14 decayed away and turned into nitrogen. So I expect decay with time in this situation. The population's getting, population as it were, the amount of carbon-14 is decreasing. Yeah, we've got an exponential function e to the negative RT, where R itself is positive. So we've got a negative exponent. With time, we get decrease. So what, about 10% of it has decreased away to become nitrogen. A more interesting use of this that we don't quite have the equipment to do yet, but we will in the next section, is, hey, if I pick up a carbon-containing material somewhere, an artifact, and it's got, say, only 90% of the carbon-14 that it originally had. The level of carbon-14 is a constant in the environment. When an organism is alive, it takes in carbon-14 and has the same level of carbon-14 that the environment has, call it Y sub 0. And when it dies, it stops interacting with the environment and the level of carbon-14 starts to decay exponentially. So if I can pick up an object and see, geez, it's only got 90% of the carbon-14 that I know it started with, I can reverse engineer this problem and conclude, yeah, T must be 866. This object must be 866 years old. So a more common application, realistically, in archaeology, for example, it's have to be a carbon-containing substance, would be to measure the carbon-14 and then use that to calculate an age. That requires an inverse of an exponential. Those are called logarithms, and that's what we'll do in the next section. But that finishes this section. So that one wasn't terribly long. Next section, we'll do logarithms, and we'll revisit this, this carbon-14 thing and tell a little algebra story about carbon-14 again. Have a nice day. I'll see you soon.